Hello everyone and welcome. My name is Saar and I want to present our paper, Fine-Tuning Giant Neural Networks on Commodity Hardware with Automatic Pipeline Model Parallelism. I want to thank my co-authors, Ido, Alon, Mark, and Assaf. So what we'll be discussing today is the workload of fine-tuning. Fine-tuning is the phase of training which follows pre-training. Fine-tuning is becoming more and more prevalent due to recent success of the approach, and DNNs are getting larger. Such neural networks, which reach hundreds, billions of parameters, have huge memory demands, and unfortunately, there is no framework for efficient fine-tuning giant neural networks on commodity GPUs. This is since many memory reduction methods have high overhead, such as swapping or sharding. The giant plus fine-tuning plus commodity scenario make such overheads even higher. For example, fine-tuning means typically that we are operating with small batch sizes, which makes it harder to hide the overheads as illustrated below, and commodity means that we are typically limited by the bandwidth of the PCIe. Pipeline parallelism, however, is network efficient. First, it can completely overlap the communication and computation. And second, it has low communication volume even for giant model. For example, in T5 with 3 billion parameters, data parallel worker will have to communicate 12 gigabytes of memory, while all pipeline workers combined would have to communicate 486 megabytes in total, and the communication would fully overlap with computation. State-of-the-art pipeline frameworks mainly fall into two categories. The first is GPipe. This is a synchronous pipeline. In GPipe, the parallelization is across micro batches. These are smaller chunks of the mini batch. And this is since in a synchronous pipeline, the next mini batch cannot enter the pipeline before all the computation of the previous mini batch has concluded. The second thing to note about GPipe is that it uses checkpointing and recomputation, which allows memory reduction. Without it, a worker would have to hold in memory multiple versions of activations, as we see for PipeDream original work, which makes it harder to train giant neural networks. PipeDream is an asynchronous pipeline, which can process several mini batches in parallel without waiting for the completion. But it suffers from the problem of staleness. Let's illustrate it and look over mini batch 1. The forward computation of it is here, and the backward computation of it is here. Between the forward and the backward computation, there is a parameter update, which means that if we want to do anything special, the forward and backward computation would happen on different set of parameters. To accommodate, pipeline use weight stashing staleness mitigation technique, which restores the parameter versions that worker 1 uses during the forward pass, and restores it during the backward computation. This means that workers would have to hold multiple weight versions. Furthermore, this does not completely solve the staleness problem. This actually, in fact, leads to a similar consistency regime similar to asynchronous data parallelism, which still suffers from staleness. We see it in several papers. So our observation SegPipe is the following. Let's present it with an example. Let's try to partition the following model, encoder-decoder model, to 3 GPUs. If each GPU may run only consequent layer, there is no balanced partition. And the implication of this is huge. Let's look at the utilization of memory of a T5 model with 3 billion parameters when partitioning with the best possible SegPipe. I want to mention that the original PipeDream partitioning, which can find the optimal SegPipe using a dynamic search, did not work, and we had to add to it a memory constraint which limited the pipeline and resulted in a bad load balance. Without our addition, pipe dream got an out of memory error. So we see that topological partitioning of previous pipeline is limited. MixedPipe. MixedPipe is our solution to the aforementioned problem. MixedPipe is a general partitioning scheme that significantly improves memory and compute load balancing while hiding communication overheads. We note that previous approaches implicitly optimize for improved and reduced communication while not allowing non-adjacent layers or operation to be placed on the similar GPU. MixedPipe relaxes this constraint and it results in much better load balance. However, such approach has more stages. Let's look. 1, 2, 3, 4, 5 stages of computation instead of 3. So would the additional stages affect the accuracy? So the answer is a two-part answer. First, MixedPipe also improves load balance in synchronous pipelines. And second, we empirically show that accuracy did not deteriorate when using MixedPipe. So let's survey the FTPipe system. The input to the system is a model, dataset, hardware configuration, training configurations such as batch size, optimizer, and so on. Our framework automatically creates a pipeline. It builds the computational graph by tracing execution, profiles the graph, then partition it using several methods, compiles the results to a code which we can run in our framework in distributed setting, then uses a simulation and analysis to compare several results. Hence, we can take the best partitioning result. Optionally, when running, we can use stateless mitigation. However, in our experiments, it was not needed, so I will not elaborate on it. So, FTPipe partitioning is an approach which uses multiple types of partitioning and simply takes the best. It searches for SegPipe solutions and for a new type of solution, MixedPipe. So let's discuss the general problem of hierarchical graph partitioning that MixedPipe solves. The general problem says the following. Given a weighted graph with weights on nodes and edges, we need to find a balanced partition to P processors while minimizing communication costs. Well, the general problem does not capture the staleness of a synchronous pipeline, and the general problems ignore communication overlapping. So let's survey the MixedPipe high-level partitioning algorithm. The input to the algorithm is a weighted graph, and what it applies is the following. First, there is a core-resting phase in which the graph is coerced to L pipeline stages, where L is chosen to limit staleness. Then there is an initial assignment to P GPUs, such as memory constraint hold, while optimizing load balance, and an uncoresting phase and refinements where blocks are shifted across adjacent stages while improving throughput, objective, or I/O. So let's say a few other things about MixedPipe coarsening. In coarsening, we reduce the size of the graph from N nodes, typically 1,000, to L. We chose the L as the sweet spot between speed up and execution, and we can see that additional stages were not needed. We coarsen the graph by merging nodes by edge contraction. First, we merge zero weighted nodes and optionally outlier edges. Second, we try to keep the CCO property, which means computation completely overlaps with computation, with the communication. We start with the smallest node and merge until we have the CCO property. And then we coarsen by type, example next slide. And finally, we coarsen around centers. So here's an example of how we coarsen by type. During the tracing of execution, we trace for each operation and layer its scope. So using common prefixes, we can coarsen adjacent nodes. This is FTPipe asynchronous pipeline work scheduler. It is an asynchronous pipeline with recomputation, but what we don't see is that it is a generalized pipeline. We pipeline the entire data flow graph, which means that we allow weight sharing, we send weights in the pipeline, stages can be concurrent, the data loading is smart in the sense that if worker 2 needs some label, it will be loaded directly to worker 2, and the data propagation is smart in the sense that if worker 0 needs to send directly to worker 2, it can do it without propagating through worker 1. So we also, by careful profiling, we make the period time of the last worker match the period time of other workers. Since it does not need to recompute, we add there more operations. So these are our results. I want to first say that we partition 3 types of models: BERT, which is an encoder-only transformer, GPT-2, which is a decoder-only transformer, and T5, which is an encoder-decoder transformer. These are the speeds up we get for word in context dataset, RTE, BullQ, multi-RC, Wikitext2, and Squad. And we see that across all data sets, FTPipe achieved faster training without accuracy loss compared to GPipe. We measure 2 matrices. First is time to accuracy, where the accuracy is set according to the accuracy of GPipe, the synchronous pipeline. And the second is epoch time. This bar plot shows the effect of MixedPipe. We can see that MixedPipe is useful for both synchronous and asynchronous pipeline. And also MixedPipe improved load balance without accuracy loss. So let's summarize. FTPipe is a system for fine-tuning giant neural networks with limited resources. MixedPipe overcomes topology constraint. We showed that it can achieve better load balance without accuracy loss. Asynchronous fine-tuning. We showed that staleness is not a problem when fine-tuning, and there are more details in the paper why this happens. We finally show up to 3 times faster fine-tuning of giant transformers with billions of parameters, and even slightly faster if we consider time to accuracy. The code is completely open source, and I want to thank my co-authors, the reviewers, and wish you all good luck.